Ladies and gentlemen, welcome to my presentation. My name is Christoph Bleicher and I am Director of the Division Structural Durability at the Fraunhofer Institute for Structural Durability and System Reliability LBF in Darmstadt, which is located in the mid of Germany. I want to talk a little bit on the influence of corrosion and also the manufacturing influences on the very high cycle fatigue behavior of aluminium bronzes, mainly used in ship propellers. Looking at the motivation, is the main topic here is that we want to make a fatigue assessment of propellers, manifolds, fittings, and other turbine components for renewable energy generation that are made of aluminium bronze, so a copper aluminium alloy that are subjected to corrosive media, which is the seawater, and on the other side to very high cycle fatigue, meaning cycles up to 10 to the power 9 cycles. We have challenges for the foundries to produce on the one side defect-free material and on the other side for the designers quantify the lifetime, quantify the loadability or the stressability, the fatigue strength to get to sustainable and at the end also a safe product for, in this case, a ship propeller. We see an example here on the lower right side. The dimensions can be something around 7 to 8 meters in diameter, and we're talking surely about several 10 tons in maximum weight. The influence parameters from the casting process can be summarized from the cooling rate. So we have different wall thicknesses here next to the mid of the propeller and to the tip of the blades, having different wall thicknesses from several 100 millimeter down to several 10 millimeters. So the cooling rate will be different due to the wall thickness, and in combination with the specific chemical composition, we might have then also different microstructures in the different areas of a propeller. The humidity of the mold material is a point that we want to consider and talk about, because the humidity and the production of the mold at the end consumes a lot of energy, and the drier the molding material is, the more energy we have to put into the manufacturing process beforehand to get it dry. And at the end, all those parameters will influence the local microstructure, including then defects, or hopefully not having defects, but at the end, the fatigue strength. In the next steps, I want to talk about the materials and the specimens, the wrought material that we cast from our project partner, which was MMG in Eastern Germany. They developed two different styles and designs of a mold. On the one side, we had something like a molding design with 2 bars where we removed the main batch of specimens having a wall thickness of 50 millimeters. You see here the casting system, the runners and the gate, the cut on both sides, and at the end this yellow, light yellow blocks and bars here were taken for the manufacturing of the specimens. On the other side, we wanted to investigate a bit the wall thickness influence. So we had a casting block with a graded or a step-like design, starting from 40 millimeters up to 400 millimeters. At the end, this will lead us, this was our hope, to different microstructures and to less defects in the lower part and the 40 millimeters. And since this is cast upright, we have a lot of casting pressure from the material in the mold, in the melt, that is putting a lot of pressure on those lower wall thicknesses here. The microstructure, the chemical composition was composed according to the IAX regulation, which is one of the standards for the design of ship propellers. And we have in the main part copper up to 82%. We are talking about aluminium in the range of 7 to 11%. We have some nickel, we have some iron, and especially the iron is a topic where we will later on see that we have also corrosional effects on the specimens. After the specimen removal, all those specimens were X-ray examined and to account for sound condition. So we didn't want to test in the first step, especially from those bars, specimen that might have a larger fraction of shrinkages. At least those that will be dedicated to be unsound and defect in when they are detected in a ship propeller later on in the serial production. There are different sizes that are definitely not accepted, and so we wanted to prevent those bars and specimens to have those critical levels of shrinkages. After the specimen removal, we made some quasi-static material investigations. Here on the lower left side, we see the results, the minimum values, maximum, and the average, and also the AX recommendation, the minimum values that are recommended. And we see that, especially in the average value, we are far above those values for tensile strength, yield strength, and also the elongation. We manufactured fatigue specimens from those batches, from those plates and designs, and we have then a batch 1, 2, and 7, which is referring to the 50mm wall thickness of those two bars that I showed you in the latter slide, and we have a batch 8, which contains specimens taken from 40mm and 400mm wall thickness from those larger blocks. Specimen is a typical fatigue specimen that we use when it comes to the test volume, 50mm in diameter, 25mm in length, but we had to account for some sealing areas here before we go to the thread for the clamping, because we need to do the tests both under ambient air and under seawater, and we need to contain and keep the seawater around the specimen, this test volume, so we installed a small container with a sealing, and so we had to also use and design some sealing areas here for those tests. Before we went on with the pure testing, the fatigue testing under seawater, we made some pre-corrosion in seawater and artificial seawater. Artificial seawater is used according to the ASTM standard provided here with 3% natrium chloride. And we kept it there for 6 weeks in accordance to DNV. So the DNV as a certification body was involved in the research project, and together with them we agreed to make a pre-corrosion of the material. And what we see at the end is here a specimen, a sound specimen, so to speak, without any pre-corrosion, and then a matured and pre-corroded specimen. During the pre-corrosion, we kept those threads and also those sealing areas clean, and we covered them so that we at the end had only the corrosion effect in the mid of the specimen. And here we see a dark color, the surface turns a bit darker. That's a typical surface for those materials in seawater. Then we come to the fatigue tests. We went for stress-controlled fatigue tests under alternating loading and tensile loading. We made the tests mainly until 10 to the power 8 cycles on the servo-hydraulic test rig, which consumed a lot of time, to be honest, because the specimens are comparably large. So we went for a 16-ton machine, and on the other side, 10 to the power 8 is a large number of cycles. And we had to do so because we wanted to investigate the very high cycle fatigue range. Under ambient air, it was not really the problem, and depending on the load level that we tested, we could use test frequencies between 5 Hz for the really high levels to prevent then some warming of the specimens. Nonetheless, in this level and fatigue level, we are talking about the medium cycle fatigue range. Probably those specimens under 5 Hz ran for 50,000, 60,000 cycles until failure. And on the lower levels under ambient air, we went on electro resonance test rigs up to 105 Hz. Under corrosion, under seawater, it turns out to be completely different. We had to do some tests under 15 Hz, once again in accordance to DNV, that we can assure that the corrosion effect has enough time and to do its job, so to speak. And corrosion is time driven, so we went for 15 hertz, which was a recommendation. It consumed a lot of time, so we're talking about several weeks for a test that goes up to 10 to the power 8 cycles. But we were curious to see what is really the frequency influence. So beside the agreement with DNB, we made also some tests on the 5 hertz and 45 hertz, so a factor of 3 in both directions, to see what can the artificial seawater do in those times. Will we have a higher lifetime when we go to 5 hertz, or do we will have a lower lifetime and fatigue strength when we go to 45 hertz? The statistical evaluation was done by maximum likelihood. That's our typical approach that we use. And when we look here on the right side, we see the clamping, upper-lower clamping. We see, we do not see the specimen in this case, but it's behind this chamber here. And we have then two smaller tubes, flexible tubes that send in the seawater, also with some air bubbles. So with a pump, we induced regularly some ambient air to enhance the corrosive effect, and simulating that the propeller and the material is partly in air and partly in the water, depending also on the payload that is in the vessel itself. Looking at the results, first of all, under ambient air, we made some tests on alternating tensile loading. We saw until 10 to the power 7 for alternating loading, not really a knee point. That was a bit surprising. We saw one for tensile loading. At the end, we stopped at 10 to the power 7 cycles here and assumed, okay, probably this will go on with this 10.9. The value for the slope in the medium cycle fatigue range further on to a very high cycle fatigue range. At the end, if we calculate the mean stress sensitivity, we come to something around 0.57 here for this material, taken from those 50 millimeter blocks. Coming to the wall thickness influence, so comparing the results from this 50 millimeter block and those specimens that we have where we have a graded or stepped wall thickness, it was really interesting that we had at the end a worse result from the fatigue point of view until 10 to the power 7 cycles when we go from 50 millimeter to those 40 millimeter specimens. Usually we say when the wall thickness is smaller, then we have a better microstructure due to a higher cooling rate, and we get then a better microstructure and a better fatigue strength. At the end, what we see is that the wall thickness was a bit better for the 40 millimeter compared to the 400 millimeter, so this upper wall thickness here, but it could not catch up with the wall thickness here from the batch 1 and 2, although the material were comparable in the manufacturing process, had the comparable chemical composition, tensile parameters were comparable. So at this stage, I could not really figure out what was the difference, but that's the result that we saw, and we'll further on investigate this effect. Beside the pure wall thickness comparison, we made also this comparison with the wet and the dry molding material. As I said, the humidity in the molding material and the molding material is mostly concrete. Is a bit a matter of CO2 emissions, because when I need to dry the mold before I go to a casting process, I will have to spend more energy in the production process. Why do we do this? Usually because the water that is inside the molding material will act as a hydrogen promoter, and together with the contact of the fluent metal and the molten metal in contact with the molding material and the wet molding material, we will get, we propose that there will be more pores. At the end, what we saw here, both for the 400 millimeter and 40 millimeter, was not really an issue either if we have a dry or a wet molding material. At the end, this was more or less the same, fatigue strength here. But at the end, the 50 millimeter casting process here got the best results. Now looking at the comparison of ambient air and seawater under tensile loading, we have here the results for the batch 1 and 2 that we investigated, and what we see is that, and what is not untypical under corrosion, that we follow more or less the slope. We get a bit steeper slope, but we have definitely no knee point here, and it goes down straight on with an even steeper slope than for the test under ambient air without pre-corrosion, and 10.4 value for the ambient air results. The same turned out for alternating loading, same relationship, around 10, 11 for ambient air and medium cycle fatigue range, and then something around 5 for the tests under under seawater. And here we tested even some longer values, and we get at the end, at the design value of 5 times 10 to the power 8 cycles, around 73 megapascal. And yeah, you see here this comparably steep slope, no knee point. And yeah, we get then roughly at 10 to the power 8 cycles to a comparable value for the mean stress sensitivity as for ambient air. So the mean stress sensitivity at the end is not really affected by the corrosive water, but the level as such between ambient air and under corrosion is definitely much larger. We wanted to see the frequency influence as well, and so we went on with those tests on the alternating loading. And what you see here is some specimens from a batch 7, also taken from another casting, from another sample here, from those first main design that we use from those 50 millimeter bars, so directly comparable from the microstructure, directly comparable from the casting process. And then we made some tests, and what we see here in blue are specimens under 15, 45, 5 Hertz. They match really well, first of all, with batch 1 and 2. That's what I showed you on the slide before. And the most important thing here is that both 5 Hertz and 45 Hertz test results match somehow here in the scatter band of our initial SN curve under 15 Hertz. We could not really see that there is an influence if you go to 5 Hertz. So we had early failures or late failures on the comparable load levels. So when you look closer here in these results, we have some stars here and some 45, 15, 45 and 5 Hertz results here, and also on the other side of the scatter band. So our postulation is at this stage, either testing at 5 Hertz, 15 Hertz or 45 Hertz, doesn't matter. We do not really get an influence, which is a good result. So for further tests, and we go on and we get an agreement with the certification body, it will be very favorable to test then under 45 Hertz due to time constraints and energy constraints and so on and so on. What would be interesting definitely is to see where's the upper limit for the test frequency. Is it somewhere around 50 Hertz when it starts to get when we start to have larger lifetimes? On the other side, the question is where's the level and where's the limit? Is it 80 Hertz, 90 Hertz? The larger it is, this number of test frequency, the better it is for the testing institutes and getting then earlier results, and spending more time on the very high cycle fatigue range and those results here in the regime up to 5 times 10 to the power 8 cycles. We made also some tests here on beyond 10 to the power 8 cycles, 2 or 3. We could not see a knee point. That's what we hope to see if we have something like a flattening of the curve here. But this is so time consuming and really a lot of work to get to those results under 15 Hertz. So we had to stop there occasionally. Looking at some fractographic investigations, not really a lot, but just to give you an idea, what we saw on one batch is that we get after the pre-corrosion some brown points here, and turned out that especially they get larger when we take the pre-corroded specimens, make the fatigue test. Then those points get larger and act as initiation points for the fatigue failure failure. Really small quantities of iron. We are talking about on a nominal level here around 4 or 5% of iron. Even if we go from 4.1 to 4.15, we have then those indications. So it's still in the specification, and the fatigue strength did not change, but we could see that there is a change in a little bit in the microstructure and the corrosion signs that we see on the surface when we have really small quantities more of iron in the alloy, which are subjected to regular imbalances in the manufacturing process, but are still within the specification. And we kept this range really short. So if you remember, the specification from IX is going something around 4 to 7% of iron that are allowed in the alloy. Here we had changes and indications of those corrosion effects when we changed from 4.1 to 4.15 or something. So really small changes got us then to more or less corrosion signs here on the surface. At the end, the fatigue strength that was most important was not really affected by this additional indications here. Looking a bit deeper on those indications, we see this here on the surface and also on the fracture surface. When the crack starts on those points and propagates, and we get then seawater into the crack surface, we have those indications here. And this is not really surprising because we get then the contact of the material to the seawater. That's what happens at the end when those parts, the medium and the fracture surface, get in touch. We did also do some metallographic investigation. They are not finished yet. We need to take a closer look on this. What we could see between the different batches that we removed from the 50 millimeter casting design, that we have sometimes changes in the alu-copper phases and the grain size. And we have some smaller crack-like indications on batch 2 and sometimes also batch 7, but they did not really lead to a significant loss in the fatigue strength, which was good and showed that even smaller signs and indications will definitely not influence the fatigue strength and the integrity of the complete product. And so we could evaluate this S curve in one parameter set. And if you remember, the scatter bands going up to 1 to 1.2 or something, this is really in the specification of a typical cast material, so there's nothing to worry about in this case, we would say. So at the end, a result, we will look a bit deeper into that in the next month to get some more information and also get a bit more information about the influence of those iron phases, getting us those signs on the surface after the pre-corrosion. Yeah, let's summarize my presentation. During this investigations, we took a closer look on those copper 3 bronze alloys, aluminum bronze materials. We showed some SN curves, investigated the influence of the manufacturing process when it comes to wall thickness, when it comes to humidity of the molding material. Also, a change in the casting design was evaluated. At the end, we have some points where we say, okay, we have no knee point under corrosion. It's not surprising, but we had also no knee point for the alternating loading tests under ambient air, which was a bit more surprising. We have a bit slightly reduced mean stress sensitivity under corrosion. And we made the fatigue tests under 15 Hertz. This was the basis, but we tried also to see what happens under 4 and 45, and there we can state nothing happens in the elongation or shortening of the lifetime of the specimen. So for the next steps, we will look a bit more and closer into those microstructural investigations. This is still an open point. And then we will come up with an additional report and see if we can, from this point on, make further improvements in the casting process to get a bit more and higher fatigue strength on the one side, and also come up with a design concept for those ship propellers. So far, I want to thank the partners for working with us in the project, MMG, and also for the funding, our German Federal Ministry of Economic Affairs and Climate Action. And I thank you very much for your kind attention and hope this was interesting for you. If there are any further questions, you can get in touch with me. Thank you very much.